Welcome to homework.
This is the answer to Chapter 14, problem number 53 from the Smith Organic Chemistry textbook. And this problem asks us two things. It's in two parts. So for A, we're asked how many signals does dimethyl fumarate, which it then spells out for us, exhibit in its carbon-13 NMR spectrum. And then part B asks us to draw three different isomers of dimethyl fumarate with given numbers of carbon-13 NMR peaks. And so the first part, for part A, we're asked how many signals this molecule would exhibit. So I've drawn the molecule here. And basically, in order to determine that, we need to know how many different types of carbons it has. And so this is going to be one type, these methyl groups. And so even though there are two of them, they are only a single type. The carbonyl carbons are going to be a second type. And then the alkene carbons are going to be a third type. And so we have three types of carbons here. And so the answer to part A is going to be 3 signals. So then for part B, we're asked to draw 3 different isomers. And so for the first one in part B, we're asked to draw an isomer with 3 carbon NMR signals. And so, of course, our original fulfills that requirement. But we're asked to draw an isomer, and so an easy way to do that is going to be just to go from cis to trans, from trans to cis. So we started with trans, so we could instead just draw the cis version, which is going to look like this. CO2, CH3. And so this will again give us 3 signals for the same reason that we figured out in part A. There's 3 types of carbons here, so that's going to be 3 signals. So next we're asked to draw an isomer that's going to give us 4 signals. And so a way to fulfill that is going to be to put both of the carbonyl groups on one of the carbons. So in part A and the first one that we drew in part B here, the carbonyls were one on each carbon, which made for symmetry across this molecule in both cases. So if instead we put both of the carbonyls on one of the carbons, that plane of symmetry is going to go away. The molecule will still technically be symmetrical, but since it will be symmetrical through a plane that runs through both of the alkene carbons, they will be different. And then, yeah, okay. So there we go. And so when we do it this way, we have one type of carbon here and here, a second type of carbon here and here, a third type of carbon here, but then this carbon on the other side of the alkene is also, a unique carbon now. So this is 4 signals here. So then lastly, we're asked to draw a constitutional isomer that is going to give us 5 signals in the carbon NMR. And so this is actually pretty challenging, and I believe that the only way that we're going to be able to do that is going to be to draw something that looks like this. So this, oops. There we go. Okay, so let's see. Okay, so in this case, we have one type of carbon in our carbonyls, a second type of carbon here, a third type of carbon here, a fourth type of carbon in this methyl group, and then I'm gonna reuse green, but please don't be confused. I'm not trying to say that well, you know what? I'll reuse blue. I'm not trying to say that these two tertiary carbons are equivalent. I am just out of colors. Okay, so there we go. And so that is 5 different types of carbons here. And so 5 different carbon NMR signals. Okay, and so again, the way to answer this problem, we just need to know how to identify different types of carbons in a molecule and realize that each unique carbon or type of carbon is going to give rise to a different signal in carbon NMR spectroscopy. And that's the answer to chapter 14, problem number 53.